You may remember or not the ending of the previous lecture when I mentioned that most problems and approaches could be understood as the search, as searching. And I mentioned that computers are very fast, so they are good at searching large numbers of solutions. And at the end of the previous lecture, I also gave you this example of searching for a shortest route between 2 points, like in navigation or GPS. And I mentioned that this could be solved by simply searching through all possible paths. And this would be very along the lines of what computers do best, because they search. We did this comparison between computers and humans, and we know that computers compute very fast. But I also mentioned that this problem could be solved by searching for a brain, and this was a metaphor, a brain that would solve such a problem. I didn't necessarily mean a brain per se, like a brain made of neurons, although it could be like this. I also had in mind something like let's call some logic that solves, like a procedure or a program that solves such a problem. So something less complex than a brain, but still something completely different than just a path. Some logic, some algorithm, some approach. And this could still be a search. So a computer would search for some logic. By logic, I mean some procedure or some algorithm, okay? So this is what I meant by saying that search doesn't necessarily mean that we are searching for something very, very trivial, but it could also be something that humans would consider very ambitious and advanced, like a prescription on how to solve a given problem, not just a single solution to a specific problem. So, optimization. How to find good or best solutions in real life. I think I don't have to mention why we are doing this. We want to save time, we want to improve quality, we want to decrease cost, and so on. In hard problems, actually in any problems, but if a problem is simple, we are not usually so interested because it's trivial to solve it. And this is important. Without the need to be an expert in solving each particular problem, and without the need to be an expert in the domain of the problem. So this is the most important for us, and this is why I'm teaching you optimization, and this is the power of optimization. You don't need to be an expert in each particular domain when you are performing this optimization. So you will see in a few slides, whatever domain is, the same approach and the same tools will be used. I think you have a gist of this because of laboratories and mathematical programming maybe. We will see. Okay, a few introductory definitions. First of all, you might have heard about something which is called decision support, or maybe not. The goals of both of those disciplines is more or less the same. It is to find the best decision or find good enough decision. But there is a slight difference, even though the goal is more or less the same. In optimization, we usually have to deal with a huge number of solutions, of potential solutions, like huge number of logics, or huge number of algorithms, or huge number of brains, or huge number of paths. And by huge, I mean something which is almost incomprehensible for a human. In decision support, we usually have much less to choose from. Like, for example, we have to choose one best decision out of 50, or out of 15, or out of 100. So usually, the number of potential variants we choose from is smaller here and higher in optimization. So this is one difference. Another is that in decision support, we focus more on the decision maker, the so-called decision maker. So a human. So this is more like, it focuses more on psychology and how humans make decisions. So the whole process of choosing the best decision here is to make this decision maker, make this human aware why he actually wants to choose this particular decision as the best. Or it's often called a variant. Here we usually speak about solutions, and here we speak about variants to choose from. But it means the same, just naming is slightly different. And so in decision support, we usually build or try to formalize a model of preferences of this decision maker. So we are trying to build a mathematical model or some algorithmic model of what this decision maker actually prefers. And we usually ask a lot of questions. This human, this decision maker, is asked a lot of questions. Why do you prefer this? Why do you prefer that? And this is why this model is constructed. And then, in accordance with this model, we choose the best variant from the set of possible variants. Okay? So this, comparing those two, we would say that this one is more human-centered. And the whole process is often interactive and iterative, so it takes a lot of questions. And it's like we are making this human aware what he really wants and why he really wants. And we are showing this mathematical model to a human so that actually at some point this decision maker agrees that, okay, this is what I want, and now I understand why I want this, and this, my choice is objective, and I believe that this is the best. In optimization, since we have so many solutions, like I mentioned, huge number of solutions, we cannot employ a human. We cannot employ a human to evaluate trillions of solutions, because the human would get tired very quickly. So in optimization, we need to employ a computer to evaluate solutions just as a human would do it. So we have to somehow move this decision making to a computer algorithm that will be evaluating these trillions of solutions. So this is more or less the difference. The goal is the same as I mentioned, but I hope that now you feel this difference. Also, what I mentioned here is like the extremes. So like I talked about pure optimization and pure decision support, but of course there are cases where in decision support we have thousands or tens of thousands of solutions, and sometimes in optimization we have very low number of solutions, like 1,000. So I mentioned the extremes, but of course this boundary is very fuzzy between those two. Okay. So some definitions and some terms we will be using. What's the optimization problem, an instance, and so on. And probably I will start by giving the most popular example of the traveling salesperson problem. You know this? Find the shortest path, traveling TSP. Have you heard this ever? You heard, and others? You didn't? Maybe raise your hand. Who ever heard this abbreviation? Oh, more or less half, okay? So I will need to explain. We have a set of locations, and we are looking for the shortest or the cheapest cyclic path. So a path that visits each city. So this is more or less the formulation of the TSP. And this is what we call a problem. A problem is defining what we are dealing with, what's our goal, what's our input data, but not what is our particular data, like particular distances between each city. We only mention that we have, for example, given a matrix of all distances. We don't necessarily mention particular values in this matrix of distances. If we mentioned particular values and we mentioned what is the exact number of those cities, we would have an instance of a problem. So a problem is like a general formulation, and the instance of some problem is specific values assigned to this problem. Do you understand this? I think this is very intuitive, and this name, instance of a problem, is quite proper. I think it shouldn't be a problem to think about those two terms, problem and instance of a problem. Then solution space. What is solution space and why this is called a space? Sometimes it is called a set of solutions, and this is perfectly fine to speak about a set of solutions. A set of solutions is simply all the solutions that exist for some problem. For example, in TSP, when we are looking for this shortest cyclic path, all the possible paths that could exist, like some very strange path, like this, I have drawn another path, this would be another solution, another potential solution. This is not an optimal solution, because this path is not shortest, but it is still one of the solutions. So the set of solutions is simply the set of all potential possible solutions to an optimization problem. So this is a set. But why do we often speak about solution space? What's the difference between a set and a space? As you probably know from mathematics, a set is just a set. It's a set of solutions, and we do not have any other particular relation imposed between those solutions. They are unordered. The order doesn't count. They are not in any relation with each other. It's just a set, like a jar with balls, which you put inside. You do not distinguish between what order they are in this jar, and so on. It's just a set. You know from mathematics that when you have some object, an object can be in a set or can be outside of the set and nothing else. When we speak about space, about solution space, we also have in mind some topology. That some solutions are placed closer to others, and some solutions are placed like further. Or some of them are more similar to each other, and some of them are more different. Okay? So we have in mind that, like I mentioned this jar with balls. So you could imagine that you spill out all those balls on the floor, and you arrange them in some particular configuration, or some topology. So space is like ordering those solutions in some way. We do not say in which way, but we have some relationship of similarity or dissimilarity. So each solution is similar to others or dissimilar to others to some degree. Do you understand this difference between set and space? Okay. We will need this space in the future. What is evaluation criterion? Evaluation criterion is simply some function that will evaluate each of those solutions. So each of those solutions will get some number, like a real value, like 7, 15. So we would imagine that solution is a function, like a function. An argument to this function is one solution, and this function will give us some value, how good this solution is. So this is evaluation criterion, very simple. But in some problems, you may have many criteria. Like you may have function f1, and you may have completely another function f2. This other function will take as an argument the same solution, but will give another value. And we may have another criterion, f3, the same solution as an argument, but another value. So this is where we speak about multi-criteria optimization. We have multiple criteria. Imagine this TSP, when we are looking for the shortest path, shortest cyclic path. So we visit each city on our route. And all the time I mention shortest, shortest, shortest. And usually when you go on some trip, on some business trip, you may be concerned with the length of this route. So you really are looking for the shortest route. But if you are going on vacation, maybe you have different criteria. What do you want to have on your route when you go on vacation trip?
Pause the video and try to answer this question.
Eventually shorter to the destination.
So length, but also points of interest, something like this. Number of points on your path. So apart from length on each edge between each pair of cities, we would have another kind of data, the number of interesting places on each edge or on each route or each road between two cities. And you can imagine that we could devise a higher number of criteria, like for example safety of each of those roads, and so on and so on, comfort maybe. Also I mentioned length, but also price. Right? You may want to minimize price and so on. So you may have many criteria, and each criterion evaluates or is able to evaluate any solution from this solution space or solution set. So this is evaluation criterion. What's a goal function? A goal function we could understand as some aggregation of those criteria. It's like a single value. Actually, if we have multiple criteria, we shouldn't attempt to merge them into one function, but we may, for example, add all those individual criteria, which is not recommended, but we could, to create one goal function. So goal function is like a general term, and we usually assume that it is a single value. We want to maximize or minimize the goal function. And algorithm is some procedure which will do this work, which will actually find the solution we are interested in, like the best solution, the cheapest, the highest value for us. So this is the optimization algorithm. So this is a more formal notation. We could imagine that our solution is described by a vector of numbers. For example, it could be like this. And we use this bold X to represent a vector. Why this is bold? In mathematics, when something is bold, it usually means something special. You could imagine that we have many X's, and those X's got like composed of these bold X, ate those tiny X's and became bold. So when you see a bold letter, you have to pay attention, because this usually means that it's not a single value like a scalar, but it can be a vector or a matrix, something bigger than a single value. Then we have this goal function or evaluation criterion. It could be called Z or whatever. It's some function, and as I mentioned, as an argument, this is our argument, a single solution. An argument to the goal function is a single solution. And then we may have constraints. What are constraints? Constraints are usually something ugly for us as people who have to deal with optimization. Constraints, as the name suggests, they exclude some solutions. They exclude some solutions as unfeasible or unacceptable for us for some reason, for whatever reason. For example, we could imagine that those x's are real numbers, okay? But we would like to exclude some particular configurations of those values, because for some reasons they are impossible to realize, they are impossible to implement in real life. It's not possible to build such a solution in real life. Or somebody would be very dissatisfied and he simply rejects such solutions. So we don't like constraints in general because they make solving the problem more difficult. But they exist. We cannot avoid them in many cases. If we can avoid constraints, we usually want to avoid constraints, but they are simply the part of our reality. Okay, so on this previous slide, what we saw here could be called a numerical optimization problem. When I say numerical, I mean this is because it's from continuous mathematics or from discrete mathematics, but they are still numbers. Numerical because we have numbers here. But we have another group of optimizational problems which are called combinatorial. And do you remember this field of combinatorics from school? Combinatorics? You must have had this in school. So we have numerical optimization problems and we have combinatorial optimization problems. And the difference is that combinatorial optimization problems usually have solutions which are composed of many elements in some specific order. So it's like mixing those balls, for example, in different orders. There was this other thing, permutations and combinations, yeah, as a general term. Maybe variations, yes. Repetitions, and so on. Okay, so this is combinatorics. And this is slightly different than numerics or numerical problems, because the solution is no longer expressed as a set of numbers, but as some combination of elements. It's not a big difference from the point of view of optimization, but it's nice to know. For example, our TSP problem, when we are visiting cities in some particular order, this could be encoded as a permutation. For example, if we, it could stay. If we called our cities with letters like A, B, C, D, E, F, then we could encode any solution as a permutation of those letters, right? F, D, C, B, E, A. This would be, and then going back to F. This would encode, this permutation of letters would encode some solution to a TSP problem. Some path, some cyclic path. So if we are speaking about combinatorial problems, then we have exactly the same situation, but this argument is not a vector of numbers, but some combination of elements. That's the only difference. And did you ever heard about this NP-hard issue? NP-hard? NP, P, and P? No?
I think it's something which can be solved in a limited time to a numerical method.
Yeah, it has something to do with the complexity, and this is what I mentioned at the end of the previous lecture, that we will start speaking about complexity of problems, and if computer is fast enough to actually search and search through this huge space of solutions, I mentioned trillions of solutions, and find the best one. So this is why we will shortly speak about complexity, or maybe not so shortly, it depends on how good you will be at answering my questions. So now we are asking whether a computer is fast enough. Is fast enough or it has enough memory to deal with this problem and to find the best solution. If this is true, then we as humans probably would be happy because we would be able to get the best solution to most difficult problems without much effort from our side. We would just let the computer do this difficult work. So when we are evaluating complexity of problems, we usually consider two criteria, time and memory. How much time will it take to find the best solution in this huge set of solutions, and how much memory a computer will require to do this job. And today, we are usually not so much concerned with memory, because computers have a lot of memory. And the algorithms that are solving those optimization problems usually do not need much memory, usually. Sometimes, indeed, memory is a problem, and then we are concerned with memory complexity, but for most cases, what is the problem is time. We are mostly interested in time. How much time? And so now I will ask you a few questions regarding three possible cases, three possible scenarios. First is pair comparison. Imagine you have some set of objects. I'm drawing circles here. We have n balls, and for some reason we want to compare each ball to each other ball. So we want to compare all pairs of balls. It's like, for example, there is some company, a company has n employees, and for some reason, the boss of the company wants to do some competition between pairs of employees. And the question to you is, how many pairs there are among n objects? How many pairs we have among n objects?
Pause the video and try to answer this question.
Divided by 2? So you have many ideas. One idea was n divided by 2. Another idea was n factorial divided by 2.
We need to just put the workers into pair, or find all possible pairs of workers.
I'm just counting how many possible pairs there are. How many? Only how many pairs? How many? Yeah. How many pairs there are among n objects? So you mean the second one, n factorial divided by 2. Okay, so when I'm asking you such a question, there are two approaches to finding an answer. At least two, many more, but I will mention two. But remember, in mathematics, usually only one answer is correct, right? So you may have many ideas, but only one answer will be okay, others will be simply incorrect. So one approach is to imagine what would be the solution on a very small cases. Like, what would be the number of pairs if we had two objects? What would it be? 1. The order is not relevant, okay? We are not taking into account ordering. So Alice and Bob versus Bob and Alice, it's still the same pair. What if we had 3 objects? How many pairs there are? It's like a triangle. If we had 4, 4, 5, 6, and so on. So this is one approach. You are looking at this very long and very hard, and try to guess what is the proper formula, and then you are checking if your prediction was right once you suggest some formula. So this is one way of approaching this, and now you can see if this is correct, if this is correct or this is correct. Both of them are incorrect, right? Unfortunately. So you didn't give me the proper formula. So this is one approach. Another approach is to imagine in your head some graphical maybe graphical or some imaginative representation of this problem. How would you actually imagine this in a more general way? Maybe some geometrical interpretation that would immediately give you the proper formula, actually. I will show you what I mean later on. Now I will just give you a little bit more time to devise the proper formula. And why do you know this formula? It was yesterday. So it doesn't count. But okay, but you mentioned n times n minus 1 divided by 2. And we can verify whether this is correct. And is it? Seems correct. But checking this may not be enough. You would need to prove that this is correct. So you have to argue and justify why this particular formula is correct. Like if you had to explain why you have this formula in mind and why it works to somebody else, and this somebody else would tell, but tell me why, explain, why did you come up with this formula? So you have to explain it somehow to prove that you are right. Okay, so it doesn't count because you had this already. Okay?
Yeah, sorry.
Yeah. So this is like you have columns and rows for each object, and you can put crosses for each pair. So if you put n squared, this would mean each pair including pairs with himself or herself, with oneself. So you subtract n, this is like subtracting this diagonal, and then you divide by 2 because I said that the ordering doesn't matter. So this is something that would convince anybody that you are right, that this formula is right. Okay? Now another case. Selection of a subset of features. So we have a similar situation. We have n objects, again n objects. And now I'm asking you, what is the number of all possible to imagine subsets of a set of n objects? So again, you have a jar with balls, and you are picking some number of balls. You can pick all balls, you can pick none of the balls, and you can pick 5 and any 5. What's the number of possible subsets of balls that you can pick from the jar, including taking all and taking none of them? Well, this is again combinatorial question. You probably remember from school all those exercises with black and white balls. Here we have a simpler case. We don't have black and white, we have all the same balls. We are just asking in how many ways you can pick a subset of those balls.
Pause the video and try to answer this question.
So we can go the same way as before. First, imagine simple cases, like what would be if we had one ball. How many subsets can we have if we have one ball in a jar? It can be that we don't take any balls, and it can be that we take all, which is 1. So we have at least 2 cases. Are there any other possibilities? No, because we have only one ball. Now, what about the case when we have 2 balls? We can take none, we can take both. So these are 2 possibilities. And what else?
Pause the video and try to answer this question.
Pick any of them, like 1. So we take this or that. So how many possibilities? 4. What if we have 3 balls in a jar? We can take none or all. We can take this, or we can take this, or we can take this, or we can take this pair, or we can take this pair, or we can take this pair. 2 plus 3 plus 3. And so on. So this is one approach. Another approach is imagining, like you had this square before for this question. Imagine some geometrical or some kind of interpretation for this problem that would prove that you are right. Because looking at this, what formula would you suggest? What would be the formula that fits this progression, this sequence of numbers?
Pause the video and try to answer this question.
So you mean a sum. It's easy to verify, right? Because you have three initial values here, so you can evaluate your idea. It will be either right or wrong.
I think it's wrong. It's right.
So this is wrong, because it should be 3 here.
It's not just 2 to the power.
2 to the power of n. Would it work in our case? So your idea was actually 2 plus sum, and this was wrong. Your idea is 2 to the power of n, and does it work? Looks like it's working.
Yes, but I don't know if it's working
In the future.
in the future.
Yes. So that's like our first guess. It seems to work. Now we would need to prove, to explain to somebody why this formula really works or not. What is this formula 2 to the power of n actually? 2 to the power of n means 2 times 2 times 2 times 2 times 2, and this is repeated n times, right?
But I think that n times is from the
Balls.
amount of elements we...
From the number of balls, yes.
Yes, and that 2 is about...
So every time we add a new ball, we add another multiplication.
Yes, correct.
And why is it so?
Pause the video and try to answer this question.
We need to find a link between those n balls and these n multiplications of 2. If we find this link, it will be our proof that this formula is correct. So every time we add a ball to our set of balls, we add a possibility of taking it or not. So those balls actually resemble zeros. 0, 0, 0, 0, which don't take, don't take, don't take, don't take. But we could also have 1, 1, 1, 1, 1, 1, 1, which would mean take all. Or we could have 0, 0, 1, 0, 1, 0, 1, or whatever combination of zeros and ones. So this is exactly the origin of this formula. We can either take or don't take any ball. So now you feel that this is correct, right? This must be correct because it makes sense. So now the last example. And the last question. Shortest path. So this is what we have here. It's TSP, more or less. So this time we have n locations, or n objects, and we are asking how many permutations there are. So this is like a pure combinatorial question. First, we are not thinking about TSP yet. I'm just asking you how many permutations of n elements there are, according to a well-known formula.
Pause the video and try to answer this question.
Yes. So we know this classical question and classical formula without any additions. But in TSP, we have slightly different situation. We have all those paths which are cyclic, but we are not interested in which city we start from. It's just a cycle without the beginning and without the end. It's just a cycle. So this may somehow change this formula. Let's again look at a few simple examples. If we have 3 cities, we have only one way of actually constructing a cycle. If we have 4 cities, we can go either this way. So for n equal 3, we have 1. For n equal 4, we have 3. For n equal 5, I don't want to draw all the possibilities. Some other number, we don't know yet. For n equal 2, we probably also have 1. let's see if this formula works. 3 factorial is 6, and it should be 1, so something is wrong. 4 factorial is 24, and it should be 3. So this is definitely too high. We have to make it smaller. And there are 2 reasons why this is too high. I gave you a hint. First of all, we don't care. This formula, this n factorial, if it had 3 elements like ABC, it would be ABC, BCA, CAB, ACB, BAC, and CBA. So this is 3 factorial equals 6. Okay? So this formula is right. These are all possible permutations of 3 elements. But we actually, if we have those cities ABC for some traveling salesperson, for some guy or girl who travels, 2 things doesn't matter. First of all, which city is the first one doesn't matter for them. And second, it doesn't matter whether they go in this direction or in the other direction. So this is why 6 possibilities actually become 1 possibility. Do you understand this?
So
Now the question is how to modify this n factorial so that it gives us these smaller numbers.
So it's something like each city can be visited only once?
Yes, each city can be visited only once, but this is what this permutation already provides and preserves. We do not need to worry about this. This city is visited only once, so we never see any letter twice in this sequence, right? We don't see AAC, for example, or ACA, or ABB. So this is not where we should look for modification. We have to make this formula smaller somehow. So first of all, it doesn't matter which city we start from. For this regular formula, it does matter, but for traveling salesperson, it doesn't. So
Pause the video and try to answer this question.
we have 3 cities. In general, we have n cities. So we should simply divide these by n, right? Because there are n times less configurations that we distinguish, or paths that we distinguish. Yeah, but do you see why? Do you see why we have to divide by n? Because there are n cities, and for this traveling salesperson, it doesn't matter which city they start from. And for this original formula, it does matter, as we see. So we are simply like removing 1 element. So you said right that this is n minus 1 factorial. Would it be consistent with this? For n equal 3, it would be 2 factorial, which would be 2, and we have 1, so it would be too much. And for n equal 4, it would be 3 factorial, which would be 6, and we have 3. So it's again twice too much. And why twice too much? Because I mentioned that the direction in which we are going is also not important, whether we go clockwise or anti-clockwise, in this or in that direction. That's why we simply divide it by 2. And now it's correct, at least for these 2 cases, but we believe that this is correct because we can justify this formula. We can explain exactly why it is like this and how it was created, how we achieve this formula. Oh, and by the way, we also know that if somebody ever wanted to distinguish between the direction where we are going, like clockwise or anti-clockwise, they shouldn't divide this by 2 if they are interested in the direction. So if this is an undirected path, we divide by 2. If this is directed path, we do not. Do you understand this? Or should I explain? Cool. N minus 1 factorial and optionally divided by 2. So we have 3 formulas. And those formulas actually tell us how many solutions would it be if we have n objects in all those 3 examples. Let's now plot a chart. On this axis we will have n, and n stands for the size of the problem, the size of the optimization problem. By size I mean the number of elements that we have to deal with. So the higher the n, the more elements to combine in all possible configurations. So the problem becomes more and more difficult because it has more and more elements. And on this vertical axis, I'm supposed to put the number of solutions. So this is, if computer was stupid and if computer wanted to evaluate all possible solutions, how many of them there are. So this is actually this number. So a number of solutions for n objects. So I simply need to draw those 3 functions. This is how this function is called in mathematics. Such kind of a function where when we have n squared.
Pause the video and try to answer this question.
It's a polynomial, right? A special case of a polynomial of the 2nd degree. And what is the name of the geometrical shape that corresponds? It's a parabola. So I will write it here. It's n squared. How is this function called? 2 to the power of n?
Pause the video and try to answer this question.
It's an exponential function, simply. An exponential function. And where should I draw it? Somewhere here or somewhere here? Does it grow faster or slower than? Faster than this polynomial. So I will draw it like here. And finally we have this factorial. Should I draw it here or here or here? Does it grow slower or faster than this exponential function?
Pause the video and try to answer this question.
It looks more scary because it has the exclamation mark. So this must be scary. You have to pay attention to this function. There are some functions with double exclamation mark as well. Okay, so why it grows faster? Because each time we add n here, we multiply by 2, right? Each new n means multiply by 2. And when we add n here, when we increase n here, we actually multiply by n. And this n grows all the time. So this is why factorial grows faster than any exponential with this constant base. Okay, so we have this factorial. And based on this graph, we see three families of functions: polynomials, exponentials, factorial. There are a lot more. Where would we put a linear function? A linear function like a times n. This would be a linear function. This is also a polynomial, this with first degree. So it's like a, like a constant, times n to the first power. Where would we put it?
I think it's slower than exponential function, but faster than polynomial.
No, because this is n to the power of 1, which means we have, it's simply, this value on this vertical axis is simply proportional. This is this coefficient that tells us how proportional it is, proportional to this horizontal axis. Then we could have square roots. Square roots, it would be something like this. We would have some other, like cube roots. even smaller. Each of them grow, but slower and slower and slower. Here you would have n to the power 3, you would have n to the power 4, here you would have 3 to the power of n, so higher the degree of an exponential. And there is one function missing, very basic, a times n to the power of 0. N to the power of 0 is 1. So what we are missing in this chart is a constant function. A constant function would be simply a horizontal line. It doesn't grow at all. And of course it would be difficult to imagine problems which become simpler as the size increases, but if we had such problems, then this line would decrease as well. Okay, so we have a chart which shows what is the growth of the number of solutions when the size of the problem grows. And we roughly can say that we have a family of exponentials here, a family of polynomials here, and factorials. We also may have functions like n to the power of n, and actually any function you can imagine. But so far we focused on those three cases. Now let's think about another kind of a chart. Time to find optimum. Time to find optimum. So the same kind of a chart, on the horizontal axis we have the same thing, size of the problem, but on the vertical axis we have time to find optimum. By optimum I mean the best solution. Time to find the best solution in this set of solutions. So in this top chart we have like pure combinatorics, and on this chart we assume that we are employing some algorithm that will actually find this optimal solution. So we are asking how much time will it take. And there is one algorithm which is the most stupid and the simplest, and I mentioned it many times. This is the algorithm that simply checks every solution, enumerates all the possible solutions. This algorithm is called exhaustive, or full search, or brute force search. There's many names, but it's always the same. It's always evaluating all the solutions. So if we used this algorithm, then this chart at the bottom would be exactly the same as the chart at the top. And you understand why? Because the algorithm would need to generate and evaluate all possible solutions. So it would surely find the best solution, and it would find the worst solution as well. It would know everything because it would evaluate all possible solutions. But we may have a smarter algorithm. So in some cases, we may have a problem which has 2 to the power of n possible solutions, but the algorithm actually, the smartest algorithms that humans devised, would have, for example, linear or square complexity, so n squared. So the number of solutions grows very fast, but the complexity or time required to find the optimal solution is much lower, because this algorithm is so smart that it managed to do something special with this problem, and it takes much faster to find the optimal solution. I will give you an example of this smartness. If we had special case of the TSP problem where we knew that all the cities are arranged in a line. Let's draw a line. It would be like a linear TSP. We know that all the cities are arranged in a perfect line. We would still have this number of possible cyclic paths. You could still go in a very convoluted, complex way, and it would be some kind of a feasible solution to go in this convoluted way. But since we know, so the number of solutions would be more or less n factorial with slight modifications. But since we know that those cities are on a line, we know what is the optimal, the shortest path by our logic and by our thinking. And what is this path? We would need to sort those cities if they are not sorted already. We would need to sort them and then simply go along this line and then come back. And we would probably be able to prove this mathematically, that this is the shortest path. And if somebody, so if somebody gave us those cities, but they were unsorted, we would need to sort them geometrically, and it would require some time to sort them. Probably faster than n squared, so maybe. So the number of solutions would grow like this, and the complexity of our algorithm would be much lower. But if somebody gave us those cities already sorted, and somebody will tell us, okay, I'll give you 100 cities, they are already sorted geometrically or geographically, and they are linear, they are arranged in a line, and give me the shortest cyclic path. How much time would it take us to generate this shortest path? We would do it immediately, right? We would tell him, the order you gave me those cities in is exactly the order you should visit those cities in. So actually, it would be a constant time, right, to give this optimal solution in this case. Even though potentially we would have this factorial number of possible routes. So I'm saying all this to show you the difference between number of solutions and the complexity, time complexity of the algorithm that gives us the optimal solution. It may be the same, those graphs may be the same. For example, if people are unable, or scientists are unable to devise some smart solution to a problem, then unfortunately they will have to inspect every solution to find the optimal solution. Then those charts are the same. But if we have some smart algorithms that can reduce somehow, we can tilt those curves, those functions slightly towards lower complexities, then we are very happy. And this is actually what scientists do all the time. They are trying to find algorithms so that we do not have to check all possible solutions to find the optimum. And this is what we'll be talking about as well. When you look at those formulas in a particular optimization problem, they may look, for example, like 2 to the power of n plus square root of n divided by 7n. They may be not as elegant as those. And what we are concerned with usually is this term which is growing the fastest. So now you know that factorial is the most dangerous, then we have exponentials, then we have polynomials, then we have linear function and constant function as well, a polynomial. So when you look at these complexity formulas, you usually are concerned with this fastest growing element of the formula. There is also this famous big O notation. Did you ever see such formulas? Big O and some formula inside. Probably too much for this lecture to explain this. Okay, optimization versus cracking codes. Why cracking codes? It has to do something with combinatorics. When you, for example, have a password when you set a password is just a combination of letters. For example, somebody tells you, you have to devise a password of at least 6 letters. Let's say it exactly 6 letters for simplicity. So you have some number of combinations, right? For example, here we had 2 to the power of n. Let's say we have c to the power of n, when n is the number of positions and c is the number of possible letters on each position. So there is some formula. So we could think that cracking codes and finding this, if there is a cracker and the cracker wants to guess your password, right? If a cracker doesn't have any special algorithm, they would need to check this number of passwords. Like, these are all possible 6-letter passwords. Number of letters to the power of 6. This would be this number of all possible passwords. What's the difference between cracking codes and optimization? The whole point of cracking codes and securing things is that when you are trying those combinations of letters, you have no clue, and you shouldn't have any clue, whether you are approaching this correct sequence or not. So this procedure underlying verification of passwords shouldn't give you any clues whether you are very close to this correct password or completely wrong. And that's why there is no point in using any smart algorithms, because we have no clues how far we are from this correct best solution, which actually opens the magic box, which actually lets you log in, for example, to your account. So I will show, and I will draw another kind of a chart here. Now, on this horizontal axis, we have all solutions. So it's not like this chart. We have all solutions. So it's like this space of possible solutions. These are all the possible combinations of your password. And there is only one which is correct. Others are wrong. One will let you through, others will not. On this vertical axis, I will write OK. Is this solution OK? One is OK, others are not. This is how it looks like in security. And this is how it should look like. When it would look something like this, it would be more fuzzy, then it would be terrible for security. Because this would mean that when you are trying to crack the code, you know that you are becoming closer and closer to this single correct solution. And this is actually what happened many times in the history of security. For example, some algorithms which were deciphering passwords on the server, for example, took slightly less time or slightly more time the closer you were to the correct password. So the cracker could actually measure this time and could learn how close it is to the correct password. Do you see it? So the cracker could actually optimize the password. If we don't have this leak of security, if we have such a landscape of quality of solutions, then optimization is actually hopeless because you have no clues. You have to check all possible combinations, right? So there is no algorithm that can crack your code if the security is implemented properly. Okay, this was, I hope, educational. Okay, and now we have a few bullets that I will skip because this would require like probably 2 or 3 semesters to explain properly with all this mathematics which is behind it. These are techniques that are used by mathematicians or computer scientists to actually formally prove the complexity of the problem. And we have many complexity classes, like I mentioned here, NP-hard, NP-complete, NP-p, and so on. We have problems which require polynomial time. We have problems which require exponential time, and worse, and higher. And there is a boundary, there is a special boundary. And this boundary is between polynomials and exponentials. And this is for practical reasons. So we consider these problems, all these problems with actually I should draw this chart not in the number of solutions, but in time to find optimum. So this is the smartest algorithm, right? So these problems are considered easy, and these problems are considered hard. So I could draw P here and P hard here. These are two major complexity classes, P and NP, and you must remember that P are simpler, it's like polynomial, and NP, like non-deterministic polynomial, NP hard, are hard to find the optimum. These are problems which require exponential time to find optimum, exponential with regard to problem size, this was our horizontal axis, or even worse than exponential. So this is your takeaway from this very complex thing we will not be talking about, because we would spend really a lot. Remember that these are formal tools to transform one problem into another, to prove that one problem is at least as difficult as the other, and so on. And there is a number of YouTube videos here, if you ever wanted to. These are links to YouTube videos, some simpler, some more difficult to see. And this number of classes, I mentioned NP hard and P, but there are many, like hundreds of classes that mathematicians discovered and distinguished between. Maybe one more thing to mention. Because I said that there is this difference between polynomial and exponentials. If you zoom in, if you look at what happens in this when n is low, it may be that, for example, a function 2 to the power of n and n to the power of 100. Okay, you have two functions. This is a polynomial with a very high degree, and this is exponential, 2 to the power of n and n to the power of 100. So technically, we would say that this is an exponential, so this is hard, and this is polynomial, so this is easy. But for low n, it's not necessarily true. It may be the case that for low n, this polynomial will grow faster than this exponential. Only at higher n, this exponential will start to grow faster than this polynomial. Just keep this in mind, that this distinction between P and P hard is more like, it concerns more like limits of n, or on n which is high enough. It concerns the nature of this problem more than how it behaves for any specific value of n. And why this boundary is exactly here? You probably know, I didn't talk about it in the previous lecture. I didn't speak about Moore's law, but you probably know that the progress is exponential in technology, right? That every 2 years, for example, the memory capacity doubles, the memory that you can buy for the same amount of money, and the speed of processor doubles, for example, every 3 years or so. So this is this Moore's law and exponential progress. So why this boundary was put exactly between polynomials and exponentials? Imagine that today you have a computer that lets you solve some optimization problem in 1 hour. 1 hour of computational time, lets you evaluate all possible solutions to the problem, and you know that the complexity of the problem is, let's say, it's linear. So the problem has a complexity of n. Very, very easy problem. The complexity grows very slowly when you increase the size of the problem. So this is today. You wait 2 years and you buy a computer which is twice as fast. For the same amount of money, you buy twice as fast computer in 2 years. And you still have 1 hour, 2 years in the future. And I would ask you, what's the size of the problem that you can solve on this computer which is twice as fast in the future, spending still 1 hour? What's the n when the complexity is linear of the algorithm? Do you see? This is like a reverse question I'm asking you. You have the same amount of time, you have twice as fast computer. If you have twice as fast computer in 2 years' time, if you wanted to solve the problem of size n, it would take half an hour, because the computer is twice as fast. So you have another half an hour to spend, and since I mentioned that the complexity is linear, your answer is correct. It will be 2n. Everybody understands why? We have 1 hour time, we have twice as fast computer, the complexity is linear, so we can, in the same amount of time, in 1 hour, we can solve a problem which is twice as big. Okay. So what if we had a problem which would have a complexity of n squared? Not linear, but slightly quadratic. Today we solved this in 1 hour, then we have twice as fast computer. How much n could grow? I will not ask you for a specific value, but you should feel that it's not 2n. It's smaller, it's something smaller. Do you feel it? Because the complexity is higher. You will feel it even more probably when I will ask you what would happen if you had this complexity. So today you are solving a problem of size n in 1 hour on today's computer. After a few years, you have twice as fast computer, exactly 2 times faster. You still have 1 hour. What will be the increase in the size of the problem that you can solve in 1 hour? Again, a reverse question. And the answer is very precise and very easy. And the answer is hidden behind this formula 2 to the power of n. As it was hidden as well in those previous questions I asked you.
Pause the video and try to answer this question.
Today you are solving the problem of size n, so let's assume that you are able to evaluate 2 to the power of n solutions. Then you have twice as fast computer, so it takes exactly half an hour to do the same work, and you still have another half an hour to do something with your algorithm. So how could n increase in 2 years' time, so that you still spend 1 hour looking for solutions?
2 to the power of n
Plus 1, exactly. Okay? So n can increase only 1. Do you see why? Because I was writing this 2 times 2 times 2 times 2 times 2 times 2. So if we increase n plus 1, we have 1 times 2. You see now? So this is the difference. In linear problems, this technological progress gives us hope that while technology progresses, since technology progresses exponentially, we believe that in the future we will be able to solve those problems. At least we have hope. When we exceed this boundary between polynomials and exponentials, this technological progress doesn't give us so much gain. Like, for example, after 2 or 3 years, we only can increase this n by 1. And we had to wait 2 or 3 years for this, right? So not very hopeful. And finally, what happens for this, for factorial? Let's say that today we are solving this TSP problem for 100 cities. So solving a problem with 100 factorial takes 1 hour today. We wait 3 years, and we have twice as fast computer. How much can we increase n? How much can we increase the number of cities?
Pause the video and try to answer this question.
Can we solve 101 factorial in 1 hour?
Pause the video and try to answer this question.
No. So we cannot even add 1 city to this because we know that factorial grows much faster. How much faster should a computer be to let us solve 101 factorial in 1 hour? How much faster than today's computer?
Pause the video and try to answer this question.
101 times, exactly. So how many years should we wait? Since we have doubling the speed of the computer every 3 years. So 3 years plus 3 years plus 3 years plus 3 years, many years, right? So you see that factorial is really hopeless. Of course, it depends what's this number here, but still, it grows very fast. Okay, so now you probably feel why there is this difference between exponentials and polynomials, and this was probably reminding you some basics of mathematics. I will finish here, and we will continue on the next lecture. I will give you a lot of examples of optimization problems. It will be like a fast-forward presentation of many optimization problems and why they are difficult and how. So it was like, this lecture was like a theory behind optimization and theory behind complexity, but treated very lightly. We didn't go into those most difficult details. Any questions?